morning, everybody, and thanks to Professor Gomez Sancha for this very kind invitation to discuss endourological lasers and their application in prostate enucleation. In the next minutes, I'm going to give an overview how endourological lasers work, what is a laser, of course, how to use them, and some novelties regarding the topic. Starting from the definition, a laser basically is light. The reason why we don't see the light coming out of the laser fiber is that laser in endourological applications, they emit in the infrared spectrum, meaning that it's not visible. But still it is a light which is coherent amplified and has an effect. And most importantly, it is a light that has a unique wavelength, meaning that each laser is characterized by a specific wavelength, and this will have specific effects which are peculiar to each laser source. Thinking of endourological lasers, we have to consider that they are mostly based on these two elements, holmium and thulium. And the lasers we know very well, it's of course holmium YAG, but still thulium YAG is also very utilized. And the most recently introduced is thulium fiber laser. We're going to see now wide differences in terms of application for them. Few key concepts which I think are really useful to understand in order to realize how these lasers work are basically that the endourological lasers, they are applied in a aqueous medium. They work in the water. And each specific laser is characterized by a specific and different absorption by water. Holmium YAG is absorbed quite decently by water, but thulium YAG and thulium fiber lasers, they are absorbed at least 2 times to 4 times as much. And thinking of laser emissions in terms of concept, we see that the laser can emit either in a continuous emission, which never stops. This has a high thermal effect, low peak power, and it's very utilized, but only for tissues, because the low peak power doesn't make these lasers applicable to lithotripsy. Instead, if we have a pulsated emission, the same energy can be emitted in discrete pulses. There is a pause in between different pulses, which allows tissue to relax in terms of thermal dose and temperature. They have a different effect. We're going to see now why they can be used either for tissues and stones. Another key concept, which is very utilized by companies and needs to be understood by us as urologists, is that different machines, they have different total power values. So low power lasers, they are not lousy lasers. They are very useful for treating stones, and they are limited by maximum power, which arrives up to 35 watts. They can be used for prostate enucleation, but still, if you want to have a proper enucleation, medium to high power lasers are the most utilized and perhaps those who perform the best for this type of procedures. And we define a medium to high power laser whenever a laser has at least 60 up to 120, 150 watts. Let's get focused a little bit on laser functioning and specifically how laser work inside the machine. So very few technical details, which can be somehow annoying, but at the same time, I'm sure and confident they can help understanding how the laser work during the procedure. Very quickly, holmium YAG laser, it works whenever a flash lamp activates a holmium YAG rod, which emits its own energy, and it has a specifically wavelength of emission, which is the one of holmium YAG, which is amplified and reflected within the machine and eventually emitted by the laser fiber. We know that a low power laser is composed by just one of these cavities, and whenever we combine 2 or more of the cavities, we have an higher and high power machine. Thulium YAG laser is very simple. Again, very similar to holmium YAG. Instead of the flash lamp, we have laser diodes, which allows these lasers to perform a little bit differently, but the key concept is very similar in terms of functioning, and a little bit different is the thulium fiber laser that we see here. We don't have a cavity which amplifies light, but we have coiled silica fiber, which is doped with thulium ions, and that's why it's called thulium fiber laser. The light is emitted by laser diodes, which gets amplified within the fiber and eventually emitted by the operative laser fiber itself. Getting a little bit towards what's more interesting for us as urologists, and therefore getting more closer to the clinical application, let's get to see what happens when the light emitted by the laser meets the tissue. So we know that, like we said before, the lasers, they work in a water environment, which means that whenever the laser comes out of the laser fiber, what happens is that the water undergoes an evaporization process, which causes this very big bubble to form, to explode, and to collapse. So each of these lasers is absorbed differently by water, and therefore the effect they will have in terms of bubble will be again different. Another key concept we need to understand is that each laser can emit in pulses, and each pulses can be different according to its characteristics. So the same amount of energy that you see here, it can be emitted in a very short time frame, which allows the peak power to raise, which means that all the energy is condensed in a very short time and will be, let's say, more abrupt in terms of emission and arrival to the tissue. At the same time, the same amount of energy can be emitted on a longer time duration, which will be delivered more gently to the tissue. At the same time, the peak power will be lower. And this has very important effects in term and differences in terms of the way that the light interacts with the tissue itself. This is very well explained by the two different effects a laser have in terms of emission and delivery to the tissue. The first one is the photothermal effect, which is the light hitting directly the tissue and determining an effect. The second one is the so-called photoacoustic effect. The bubbles that you've seen before that forms at the tip of the laser fiber, it explodes, and that energy formed by the explosion and collapse of the bubble will determine a second effect on the tissue. And we're going to see in a while why this can be important when treated prostate and during prostate enucleation. Now, we have the laser fiber, we have the energy coming out of the laser fiber and hitting the tissue. At the end of the day, after all these technical details, what we want to know is the way that the light interacts with the tissue, which means that we want to know if a laser is good in incising the tissue. At the same time, we need some coagulation, and we want to know whether the laser is good or not at coagulating the tissue. So we want to estimate what is the incision depth for each specific laser, and at the same time we want to know whether the coagulation area is good or not. And keep in mind that high power laser, which emit very big and explosive bubble, they will be really good at incising the tissue, but at the same time we will have, due to the less gentle delivery of energy, a less important coagulative effect. Whenever you have a low peak power, it means that you will have a less disruptive bubble, but at the same time you will have more heat diffusion and better coagulation. Just to be clear, this is a tissue treated with the laser. You see that the incision depth is measurable very well from this point of view. At the same time, the coagulative area, it gives some information in terms of coagulation properties of the laser itself. Just to give some numbers, you see here that the holmium YAG laser is able to incise up to 4 millimeters according to the specific parameters you're going to use, and it has some decent coagulative profile. But still we have differences in terms of laser, like we've seen before. They can be absorbed more or less by the water, but at the same time, the pulse that is generated by different lasers will determine different effects on the tissue. You see here that we have a very tall pulse. A very tall pulse means that it has a very high peak power, a short pulse duration. It means that the energy coming from this laser, which is holmium YAG with a short pulse, will be delivered very abruptly to the tissue in a very explosive way. As you can see here, the bubble of holmium is very big and very explosive. At the same time, holmium YAG can be stretched in terms of pulse, have a lower peak power, but if we are looking for very low peak powers, we need to move to thulium YAG and also to thulium fiber laser. You see here that the bubble coming from thulium fiber laser, it is much smaller in diameter and very less explosive than holmium YAG itself. At the same time, we know that the pulse coming from holmium YAG can be split, can be stretched, and when it's split at this time, you see a double pulse coming from the first pulse causing the first bubble and the second pulse going through the first bubble in a way that it allows the energy to be better delivered to the tissue. And in a certain way, the peak power is lower, so you can imagine that with this laser pulse, more energy will arrive to the tissue, having a better thermal and coagulative effect. So do we have some way to evaluate these differences in terms of laser properties? Of course, we know that when we use them in the clinic, that the effect will be different on the tissue, but at the same time, we know that in the lab, we can estimate all those parameters. And you see here the difference. So holmium YAG, you see a very deep incision, but at the same time, the tissue is very well dismembered by the bubble and the explosion of the bubble itself. You see on the other end that the cut with thulium lasers, it is less profound, less deep. At the same time, it is a more precise incision because the bubble doesn't explode the same way that it does with holmium. But an important difference is that the coagulation with thulium YAG laser is very, very high and much higher than holmium YAG. And you can estimate these numbers and you're going to see that the incision depth is higher with holmium, but at the same time, the decoagulative area is twice as much with thulium. And just to have a quick recap of these two lasers in terms of property, you're going to see here that holmium YAG, it has a very high peak power compared to thulium YAG and also thulium fiber laser. It is a pulse laser. Thulium YAG can work, and thulium fiber laser, they can work in both continuous and pulsated way. Holmium YAG has a more explosive delivery of energy, which means an explosive bubble, which means deeper incision and dismembered tissue, but at the same time, less coagulation as compared to thulium YAG and thulium fiber laser. So we've seen before that a laser pulse can be stretched, and we can have short pulse and long pulse for holmium. At the same time, the pulse can be modulated. Pulse modulation was mainly created for stone procedures, but at the same time, it turned out to be very useful also for tissue procedures. You see that when you have a short pulse with holmium, the bubble is very explosive. When you have a long pulse, the bubble is longer and a little bit less explosive. We also know that a laser pulse can be split, which means, like we've seen before, that the peak power will be lower and the delivery of the energy will be a little bit longer and more gentle as compared to holmium YAG. I'm leaving this as a quick recap of the laser characteristics. It's a lot of numbers, and you find here the publication if you want to look at them a little bit more relaxed, but still different wavelength, different absorptions by the water. Lasers can work in pulsated ways, some of them only pulsated, some of them can work also as continuous laser. We have different ranges of pulse of energies, but what I want you to focus on is that different lasers, they have different peak power values. We've seen before again, and I want to stress this concept, that higher peak power will imply more explosive delivery of energy to the tissue, less coagulation, and more better incision depth and better dissection of the tissue. And you know, if you like HoLEP very much, and if you follow this channel, I'm pretty sure that you do, you see that in order to have this very dissective effect of the prostate from the considering the adenoma from the capsule, you will need this type of dissection that you're going to have very well with holmium and a little bit less with other lasers. Another thing is that holmium is a very modulable laser. And of all the lasers that you have on the market now, is the one that allows you to perform your procedure with a very, very, very wide range of peak power values. And we're going to see that a new innovation coming to the market will allow to lower the lowest range of peak power for holmium up until 500, matching closely thulium fiber laser. So eventually, a quick recap of these three different technology, if you want to think of them in terms of tissue application, is that holmium YAG works very well with the photoacoustic mechanisms, which implies a wider incision depth and dissection. Holmium YAG can be pulse modulated, meaning that it will have an enhanced photothermal effect and again a better coagulation. We have thulium YAG, which can work in a continuous way. It will be mostly for thermal, so a wonderful coagulative effect, but still some carbonization. And in terms of dissection, it will not be its best characteristics. Thulium fiber laser, it works in pulsated way. It has to have a photothermal effect with a minimal photoacoustic, which is due to smaller cavitation bubbles coming from this laser. And eventually, thulium YAG, it also works in a pulsated way, meaning that it could be a compromise, or let's say it meets halfway the characteristics of holmium YAG and thulium fiber laser. And with this final recap, I really want to thank again Professor Gomez Sancha for this opportunity and you all for your attention. Thank you very much.